Hi, welcome to a lecture on the directivity of a current moment. The current moment is the simplest possible distribution of current, and here's the expression for that, which has been discussed in another lecture. It is simply a chunk of current that exists only at the origin, as indicated by the spatial delta function here, having a magnitude and phase determined by the current moment, and in this case, pointing in the z-hat direction. That's the direction of current flow. And also in a previous lecture, we have identified the electric field intensity, which is radiated by this simplest possible distribution of current. And for distances which are much greater than a wavelength away from the origin, it is this relatively simple expression, recognizable as a spherical wave. Now, under the assumptions that we've already made, this radiated wave is actually approximately planar. Yes, it's a spherical wave, but remember, as you get farther and farther away from the origin or from the location of a spherical wave, the associated phase front is closer and closer to being planar from the perspective of somebody sitting at the center of this patch. So once you get far enough away, you can really treat this little chunk as if it is planar and not curved. And that's good because the power density of a plane wave is known by every undergraduate who's taken electromagnetics to be given by this expression. You simply take the magnitude of the electric field intensity, square it, divide by 2 times the wave impedance of the medium. Just a quick side note, that factor of 2, that indicates that the electric field intensity is in peak and not RMS units. If the electric field intensity is in fact in RMS units, then you would not have that factor of 2. Works exactly like voltage and current in AC systems. Anyways, you see that the electric field intensity squared has units of volts per meter squared. In the denominator, we have units of ohms for the wave impedance, so that gives us watts per meter squared, which is power density as expected. So in this case, the power density at a position R is obtained simply by substituting the expression for the electric field intensity into this expression for the power density, and we obtain this expression. The total power which is radiated is obtained by integrating over a sphere which surrounds the current moment and has a radius much greater than a wavelength. Right, so here is the current moment. Here is a sphere surrounding the current moment, and the radius of that sphere should be much, much greater than a wavelength. And under that assumption, then we can use these expressions. And the total power which is radiated, P sub rad, is then given by an integral over the surface script s. Script s is referring to this sphere here that we're integrating over. The integrand is the power density expression. And then ds, the differential unit of surface area. So ds is a little chunk on the sphere, as shown there. So we can expand this out in terms of our coordinate system. Theta goes from 0 to pi. Phi goes from 0 to 2 pi. Those are the two radial coordinates and their limits. We substitute the expression for power density that we've obtained above. And then ds, the differential unit of surface area, is given by r squared sine theta d theta d phi. You can find that in any calculus book going back to freshman level. So we make the substitution and then factor out all the constants. There they are. We can separate the integrals into an integral in theta and an integral in phi. So here's the integral in theta, and then here's the integral in phi. So right away we see this is going to be pretty simple to do. The integral in phi just reduces to 2 pi. The integral in theta is sine cubed theta, and that's a very well-known integral. The answer is 4/3, and if you'd like, you can of course confirm that for yourself. It is not hard, but it's tedious. Note that the dependence on distance is gone. And you expect this, right? Because we're talking about power radiated. And the radiated power should be the same no matter how big the sphere is. right? The same amount of power passes through any sphere, independent of how large that sphere is, right? All the power that passes through a smaller sphere also passes through the larger sphere. So we should expect that the R dependence is gone. So we put all this together and we get this expression. And always a good thing to do when you do an integration like this is to check units. So eta, impedance, has units of ohms. Current squared has units of amps squared, and so on. Beta, remember, is the phase propagation constant. That has units of radians per meter. But remember, radians are special units. They are the natural units of angle, so you can ignore them. So that radians per meter times meter gives us radians, or just nothing. We just can ignore it. So the result turns out to be watts when you put all that stuff together. Next, we can ask the question, what is the power density averaged over this bounding sphere? Right? We call that the average power density. Well, the average power density over the whole sphere is the total power divided by the area of a sphere, which is 4 pi r squared. So once again, using our expressions for distances which are far from the current moment, we end up simply with this expression, not surprising. Also not surprising is that our power density, one of our squared dependents, is back, because we're talking about now power density, not total power. So finally we get to the point. The directivity of anything is defined as the power density in a specified direction divided by the power density averaged over all possible directions. And we have now worked those two things out. We simply divide the results, and we find that the directivity depends only on theta, not on phi, and is given by 1.5 times sine squared theta. This is the directivity of the current moment. The directivity is maximum at Broadside. So although we can say that the directivity is given by this expression, frequently in this business, when we say directivity, we're referring to the maximum directivity. You kind of have to pick that out of context. But the maximum directivity here is given obviously when theta is pi over 2, that is broadside to the current moment, at which the directivity is 1.5, or as we say, 1.76 dBi, dB relative to isotropic. We get that simply by taking 10 times log 10 of this number. So 1.76 dBi is the maximum directivity of the simplest possible current distribution. So two things you should get from this. One is to know this result. It's important for a reason I'll elaborate on in just a moment. But the second is to know this procedure. You identify the electric field. From that you get a power density. You integrate over the power density to get a radiated power. You then compute the directivity as a ratio of those things. One final note here is this number, 1.5 or 1.76 dBi, is effectively the lowest directivity you can achieve. So worth knowing that when you have real-world array elements in a big array, it's unlikely that those array elements will ever have a maximum directivity of less than approximately this number. And don't confuse this with gain. Gain is directivity times loss in the radiating system. So sure, you can arbitrarily make this 0 dBi by having about 2 dB of loss within the system, but that's not what I'm referring to. I'm referring to directivity. This concludes this lecture on the directivity of a current moment.